A ramp AB of length 8 metres and mass 20 kilograms rests in equilibrium with the end A on rough horizontal ground. The ramp rests on a smooth, solid cylindrical drum which is partly under the ground. The drum is fixed with its axis at the same horizontal level as A. The point of contact between the ramp and the drum is C, where AC is equal to 5 metres, as shown in Figure 2. The ramp is resting in a vertical plane which is perpendicular to the axis of the drum, at an angle theta to the horizontal, where tan of theta is equal to 7/24. The ramp is modelled as a uniform rod. Part A asks, explain why the reaction from the drum on the ramp at point C acts in a direction which is perpendicular to the ramp. So essentially, it is asking us why this force between the drum and the ramp here acts in kind of this direction, where this is a right angle. And the main kind of reason as to why is given to us in the question, because we're told that the drum is smooth, and smooth means no friction. So there is no friction between the ramp and the drum at the point C, and therefore there's no force to kind of disrupt the fact that the normal reaction force acts perpendicular to the plane. So because there is no friction, and because the drum is smooth, there's no friction, and therefore the reaction has to be perpendicular to the ramp. And that's all we need to write to get our 1 mark, because it's only a 1 mark question, so we don't need to write lots, just a sentence to say that the drum is smooth, and therefore the reaction is perpendicular to the ramp. And this will get us the 1 mark for the question, because that was all we needed to state was that because the drum is smooth, or you could have said no friction, either works because they mean the same thing. Because it's smooth, the reaction is perpendicular to the ramp. Now part B is asking us to find the magnitude of the resultant force acting on the ramp at A. And now, as you can see, this is quite a large question. It's worth 9 marks. So it might be worth drawing some of this information we've been given onto the diagram so we can kind of visualise it a bit better when it comes to answering the question. So the first thing we're told is that the ramp has a mass of 20 kilograms, and using the equation F equals ma, force equals mass times acceleration, we know that when the force is weight, the weight must be 20 kilograms times the gravitational acceleration, and therefore the weight of the ramp is 20g. And the way we can figure out where this weight acts, because it has to act somewhere along this ramp, is we were told that the ramp can be modelled as a uniform rod. And what this means is that this weight will act in the centre. The centre being 4 metres in, as we're told that the ramp has length 8 metres. So the centre of that is 4 metres in. So if we say that this is around 4 metres in, and we draw the weight acting vertically downwards, the weight being 20g. So that's the first thing we've drawn on, the weight of the ramp, as we know it acts in the centre. Now, the next thing we're told is that the ground is rough horizontal ground. And rough means that there is a frictional force. So we're being told here that there's a frictional force between the ramp and the ground. And the frictional force will act in, kind of towards the drum. So if we call that F, just for frictional force, that's another force we've added. And we also know that because of this, because the ground is rough, there must also be a reaction force acting perpendicular to this. And if we call this RA, meaning the reaction force at A, and the reason we need to say RA is because there's another reaction force, which is the one at C, that we were using in part A. So if we now call this RC, we have 2 reaction forces, and they're both perpendicular to the respective planes. This one is perpendicular to the ramp, and this one to the ground. Now, these are all the forces that we've been told about, and we've marked them all on the diagram. But there's one more thing that we can add that will help calculations in a minute, and that is if we componentize some of these forces, being the RC and the 20G force. And the reason we want to do this will become a bit more apparent later, but if we want to be resolving vertically and horizontally, or kind of respective to this ramp, we'll need them to be resolved. So if we start with this weight, resolving would be perpendicular to the plane, which we can say is this line here. Not very accurate, but if this is perpendicular to the plane and this is parallel, we know that the one that's perpendicular is acting away, and the one that's parallel is kind of acting towards the way the weight acts. We know that this angle here must be theta, and therefore this component here would be 20g cos theta using trigonometry rules, and similarly this one is 20g sine theta because we're using the opposite and the hypotenuse, and for this one we were using adjacent and hypotenuse. And now if we do the exact same thing with RC, but this time we're resolving vertically and horizontally, whereas before we were resolving kind of in terms of the ramp. So if we first resolve vertically, we know that this is acting upwards, and horizontally will be acting again kind of towards the way that RC is acting. We know that this angle here must be theta again, because of kind of rules of angles, and therefore if this is a right angled triangle, this must be RC cos theta, and this one up here is RC sine theta. And I should also add that this weight acts 4 meters, kind of from A and from B, but we don't need to mark it on twice. So now that we have everything that we possibly could labelled on this diagram, we can now start to do some calculations. And the first calculation we can do, and this calculation will help us find the value of RC, is if we take moments about A. Because if we take moments about A, that eliminates this force and this force, because if we're taking them from this point, the distance to both of these is 0. Hence, the forces are kind of eliminated from the calculation. So if we take moments about A, and we want to do this clockwise, so we can denote that with this kind of arrow. Firstly, we want to find the forces that act kind of clockwise from the point A, and there's only one force that does this, and that is the weight. But we don't just want to use the weight, we want to use the component of the weight that acts perpendicular to the ramp, and that is because for moments, it's the distance multiplied by the force when it acts perpendicular to, in this case, the ramp. So because the equation for moments is the distance, which here is 4 meters, multiplied by this perpendicular force, we can say that the distance is 4, and then the force is not just 20g, but it's the one that acts perpendicular, which is 20g cos theta. And now this is the only force that acts clockwise to A, and the force that acts anti-clockwise to A, again there's only one of, but this time it is RC, and it's not a component of RC, because if we look, we can see that RC is perpendicular to this ramp. And we know that RC is 5 meters away from the point A, so the distance, and we're taking this away because now this is anti-clockwise, the distance is 5 meters multiplied by RC. And we know that this is equal to 0, and the reason for this is because we were told that this ramp and everything rests in equilibrium, and one of the conditions of equilibrium is that the moments about a point are equal to 0, and so we can say that these moments have to be equal to 0. So if we do this calculation and add 5RC to both sides, we're left at 5RC is equal to 80G cos theta, and therefore RC is equal to 16G cos theta. And we can actually simplify this a little bit more because we can find out the value of cos theta. And the way we can do this is using the fact that tan theta is equal to 7 over 24, which is something we were told in the question. And that means if we were to draw out a right-angled triangle and called one of the angles, say this one, theta, we know that in general, tan theta is opposite over adjacent. And therefore, if it's 7 over 24, we can say that the opposite must be 7 and the adjacent must be 24. Because if we did opposite over adjacent here, we'd have that tan theta is equal to 7 over 24. So now that we have these, we can use Pythagoras' theorem to find this last length here, the hypotenuse, and we find that this is equal to 25. So now we can use trigonometry to find out an expression for tan theta, cos theta, and sine theta. So we can start off with the one we know, which is that tan theta is equal to 7 over 24. And now if we did cos theta, in general, cos theta is equal to the adjacent over the hypotenuse. And here we can see that adjacent is 24 and hypotenuse is 25. So cos theta is equal to 24 over 25. And if we do the exact same thing with sine theta, which is opposite over hypotenuse, we're left with 7 over 25. So now that we have all these expressions, we know that 16g cos theta is the same as 16g multiplied by 24 over 25. And if we put that in to our calculator and solve it, we can find that RC is equal to 384. So if we put that into our calculators and solve, we can find that RC is equal to 384 G divided by 25. And if we just keep things in terms of G, it kind of prevents us from having long decimals that we need to write out, and we can just solve properly kind of at the end of the question. So now that we know what RC is, we can resolve upwards, vertically upwards, and horizontally to find RA and F. And that's because RC was the only unknown that was kind of stopping us from finding this. So if we start off with resolving upwards, which is in the direction of RA, if we resolve upwards, we know that the forces acting in this direction, upwards, are RA, as you can see here, and also this component of RC, which is RC cos theta. So we know that acting upwards, we have RA plus RC cos theta. And now we know the things that are acting downwards opposite to this. There's only one, and it is the weight here, which is 20g. So we can take 20g away for kind of the net force. And now this is based off the equation F equals ma. But because we know this whole system is in equilibrium, we know that acceleration is 0, and therefore this is equal to 0. And now we can do this calculation now because we know what RC is, as we've just worked out to be 384g over 25. And we know what cos theta is, as it's 24 over 25. So now we can be left with RA plus, and then RC cos theta, if we do 384g over 25 multiplied by 24 over 25, we're left with 9,216 G divided by 625, and then this is still take away 20G is equal to 0. And now if we add 20G to both sides and take away 9,216G over 625, we are left with Ra is equal to 3,284 G over 625. And now, if we do the exact same thing, resolving horizontally, kind of to the right in this diagram, which is in the direction of F, we can do the exact same thing to find an answer for what F is. So if we resolve horizontally, we know that the forces acting in this direction are just F. F is the only force acting in this direction. And then the forces acting in the opposite direction, again, there's only one of, but this time it's this component of RC, which is RC sine theta. So resolving horizontally, we know that we have F take away RC sine theta. And again, for the same reason as before with the F equals ma, where this is in equilibrium, so acceleration is 0, we know that this equation is equal to 0. And now, we know that RC sine theta is equal to 384g over 25 multiplied by 7 over 25. So we can say that this is equal to F minus 2,688 G over 625 is equal to 0. And therefore, if we add that to both sides, we get that F is equal to 2,688 G over 625. So now we have values for RA and F. So if we were to draw this triangle out where we know that RA acts upwards like this and F acts horizontally like this, the question originally was asking us to find a value for the resultant force acting on the ramp at A. And the way we can draw that is it's the resultant force of these two forces. And so the way we can find this is using Pythagoras' theorem, because if we were to draw this triangle another way, we could draw it as the resultant force being this line, the hypotenuse of these two forces. And so using Pythagoras' theorem, we get that the resultant is equal to the square root of RA squared plus F squared. We know that RA is equal to 3,284 G over 625, and then that's squared plus F, which we've just found out to be 2,688 G over 625 squared. And then if we do that in our calculator, we find that the resultant force to 3SF is equal to 66.5 newtons. And now this question was worth 9 marks. So if we go back to look where these all came from, we get a total of 6 marks for these first 3 equations that we constructed for the moments about A and then resolving vertically upwards and horizontally. And the reason we get 6 marks for that is because you get a method mark and an answer mark for each one. So kind of attempting to do it and then doing it correctly will get you 2 marks for each equation. So constructing this equation here gets us 2 marks. Constructing this equation here gets 2, as does this one. So it's a method mark and an answer mark for each. So our next 3 marks now come from, first of all, finding a value for RA, so the reaction force at A, and F, the frictional force. So getting this value and this value will get you 1 mark for getting both of them. So if we mark that on here. And now next, our second to last mark comes from over here using Pythagoras' theorem to find the resultant force. So just doing that the resultant force is equal to the square root of R squared plus F squared, as they say in the mark scheme, is 1 method mark. And finally, we get an answer mark for finding that the magnitude of the resultant force is 66.5 newtons to 3SF, or you can also give it to 2SF if you want, but either gets you the final 9th mark. So we're now told the ramp is still in equilibrium in the position shown in figure 2, but the ramp is not now modelled as being uniform. Given that the centre of mass of the ramp is assumed to be closer to A than to B, Part C asks to state how this would affect the magnitude of the normal reaction between the ramp and the drum at C. So first of all, if we're told that the centre of the mass is assumed to be closer to A than B, if we were to draw that on the diagram, it would look something like here, for example. It could be any place less than where it previously was, which was 4 metres kind of along. So if this was where it used to be, and we've now moved it closer to A than it is to B, then we know that this is now the centre of mass, where the centre of mass acts. And if we were to now take moments about A, like we did in part B, so our first step in part B was to take moments about A. So if we were to do this now with our moved centre of mass of the ramp, we would notice that the clockwise moment about A would decrease, because when we were taking moments about A, the only thing that had a clockwise moment was this centre of mass force, and the only thing that had an anti-clockwise moment was this reaction force at C, if we just label that on the diagram here. And so, given that moments are the distance multiplied by the force, if our distance between A and this point here has decreased, then the total moment of this force will decrease. And if this is the only clockwise moment acting, then the clockwise moment about A will decrease. And since we had it's the clockwise moment take away the anti-clockwise moment is equal to 0, if the clockwise moment decreases, then so will the anti-clockwise moment. And what this means is that the magnitude of the normal reaction at C will decrease, because that's involved with the anti-clockwise moment, and if one decreases, the other does. And so we can say that the magnitude of the normal reaction at C will decrease. And for this question, because it is simply state how this will affect the magnitude of the normal reaction, we don't actually have to give a reason why. It is literally asking us for to say whether it would increase, decrease, or stay the same. And so this is enough to get us 1 mark, because we've stated that it will decrease, and that is the answer.